and reduce the risks. For these kind of situations, we need of intelligent navigations, particularly for autonomous vehicles and advanced robotic applications, right? So these are the earlier days. People used to represent the navigation process like in geography and hydrography concept. They can able to navigate, right? Now, basically, what is navigation? Navigation is a field of study that focus on the process of monitoring and controlling the movement of a craft or a vehicle from one place to another. This is the basic of navigation. The field of navigation includes four general categories like land navigation, marine navigation, aeronautic navigation, and space navigation. Today, we are going to concentrate on aeronautic navigation. Okay, it is also the term of art used for the specialized knowledge used by the navigators to perform navigation tasks. All navigational techniques involve locating the navigator's position compared to known locations or patterns. This is very important because by knowing the present and past positions, the navigator will be able to predict what will be the future position. That is very important in the navigation process. That is what always we'll go for the current measurement and updated measurement to know the position of the future. Now, navigation in a broader sense can refer to a skill or study that involves the determination of position and direction of any craft or a vehicle. Right. Now, for knowing the position of any vehicle or any craft, you're supposed to know the latitude and longitude concepts, right? So for that, I'd like to play a video which will give an insight about the latitude and longitude calculations, right?
Latitude and longitude. Just like a letter is able to reach your house to your address, a specific place on the map or on the globe can be located with the help of geographic coordinate system. The geographic coordinates of a place consist of the degrees of latitude and longitude. Latitudes or parallels are imaginary lines drawn parallel to the equator towards both the north and south directions. They are measured from 0 degree to 90 degrees in both hemispheres. The earth is round, and so the length of the latitudes decreases as we move towards the poles. Longitudes or meridians are the imaginary lines drawn between the two poles. They divide the earth in 360 equal segments, like that of an orange. The 0 degree longitude passing through Greenwich in England is called the prime meridian. One half of the world is measured in 180 degree longitudes of east, while the other half in 180 degree longitudes of west. Both the latitudes and longitudes form a grid in which they intersect each other at right angles. So, for locating a place on Earth, you need to read the degrees of latitude and longitude. For example, city of New Orleans is located at 30 degree north and 90 degree west. Remember one thing. Although a few lines of latitudes and longitudes are shown on the globes and maps, their number is infinite. So, a city can fall in any one of these crossings.
So I hope. So I hope everyone got an idea about how to measure up latitude and longitude. With these inputs, we will move on to our further discussion. In fact, uh, for a current scenario, when you want to go for a navigation, as you all know, GPS is playing a very important role. GPS stands for Global Positioning System. Actually, it contains three segments. There are three segments the GPS is involved during the time of its complete working process. The first is space segment. This segment is in the space. It consists of 24 satellites. It has 6 orbits. Each orbit has 4 satellites. So totally 24 satellites are kept in the 4 orbits, which are placed at the altitude of around 28 to 32 kilometers on the space. Right? Then we have a second of the segment called control segment. It is the ground control, which is located on the earth. Then last of the GPS is user segment. It is where the user used to carry as like our mobile phone, right? Generally, GPS are divided into two kinds of application. One is civil, another is military. The difference between of these two is technically the same in operation. Only thing is military like GPS are as a precise measurement. Okay, so using this GPS, it's a satellite-based navigation. We can able to position the things of our any object or vehicles in terms of latitude, longitude, and altitude. Altitude come into picture when you have air vehicles, right? Then, uh, in case the GPS element has three segments of space, user, and ground segment. Now let us see how these three segments are get connected during the time of the GPS operation. See, the control segment consists of an antenna. It has a master control station and also it has a monitor stations, right? And the data from the this control segment will go to space segment. It consists of the data which is called as an uplink data. They are like satellite ephemeris position constant, clock correction factors, atmospheric data, albanic data. Similarly, from the space segment, it is goes to a user segment, right? The downlink data also we have information like coded ranging signals, position information, atmospheric data, and albanic data. I think these albanic data are nothing but a data which contains of the date and the positions and some of the information about atmospheric changes. All these informations are contains the name called albanic data. So like this, the GPS element is consists of these three segments and they are all working together with the coordination. We are able to get the position of any moving object in the earth. Okay. Now, this GPS, since it's a satellite-based navigation, it has some of the errors like orbit error, clock error, and ionospheric delay and tropospheric delay. Then it has a multipath error, then the receiver noise. These are the 6 errors predominantly occur during a time of your GPS navigation. I'm not going to in detail of these errors because it itself has a lot of time. Because you know, multipath is a very important thing when you go for a wireless based communication, right? And that is due to different obstacles placed in between of your transmitter and receiver. Similarly, the atmospheric ions and this tropospheric atmosphere, we have a lot of ionic particle, cosmic particle, polar particles that also will give some kind of errors. And the noise during the time of receiving, the signals got some kind of that is called an attenuation. It's called in wireless communication, it's called fading. So that also lead to some kind of errors in the GPS signal. Orbit error, clock error, they're all in the alignment of your frequencies, right? And in the orbit, your position values, that's lead to some kind of errors. So these are the errors we have in the GPS, right? And meantime, I would like to inform the participants. In the general, the uplink data frequency is always higher than the downlink data frequency, the GPS elements of operation. I think you know the reason, because when you send the signal to the satellite from the ground, the satellite signal, the signal which you are sending from the ground to satellite must be higher than the satellite signal which you are getting from satellite to ground station. Okay, the reason is that when the time of signals goes from the ground station to satellite, in the uplink process, the satellite undergoes lot of difficulties. In the satellite time, it is called as perturbations, because the ground station, it has some kind of pull from the gravitational force, as well as when the signals reach to the space, it has some gravitational pull of sun and moon. And during the ionospheric traveling, it has a lot of problems due to the ionospheric interferences or obstacles. Similarly, in the processing of your transponder, once it's received in the satellite, that transponder loss, all these losses has to withstand and have to balance that. For that, you have to select always the uplink data frequency must be higher than the downlink data frequency. I think the participants must aware of that. So with that, I'm moving to the slide of this errors GPS that also I explained. Now, since the GPS has this kind of errors, right? So we need some kind of supporting navigation system, which must be a alternative or a complementary navigation system for this GPS. That is called inertial navigation system, right? This inertial navigation system is a self-contained system that integrate the three acceleration and three angular velocity component. Here you are using all sensors kind of things to make your acceleration and angular velocity components. You know very well, acceleration sense it means of the linear displacement. Angular is the means of the variation of your inclination things. So for measuring of the accelerations, we need accelerometers, and for varying of your angular, we need gyroscopes. So using of this linear measurement of accelerometer and angular measurement of gyroscope, we have a system of navigation called inertial navigation system. All these sensors are kept in a three-body axis, because as I said in the earlier of my presentation, I am looking on aircraft kind of navigation. So there I need of latitude, longitude, and altitude. So that's the reason I need an inertial navigation system, a self-contained inbuilt system which can kept on the object. Using this INS also, we can able to navigate the particular vehicle or an object. But unfortunately, this INS system also has some kind of errors, that is called as a sensor-based error. They are like an alignment error, gyroscope error, accelerometer error, non-orthogonality of gyro and accelerometer. I think the time of latitude and longitude of measurement also we need of 90-degree concept. So that 90-degree of orthogonality can be preserved during of the entire navigation process between of your gyro and accelerometer sensors. In case you have any kind of misalignment, that leads to some errors. Similarly, when you go for a sensor-based measurement, definitely setting of your sensors in the initial phase and some maintenance that introduce some kind of noise randomly during the time of measuring. That is called random measurement noise. So these are the errors we too also have in INS. So in order to use of this GPS and INS, both are a navigation-based system, but both are has their own drawbacks. Their own errors. So what to do? We have to go for a integrated system which can complement to each other. See here, the alignment means since I used of the aircraft kind of vehicle, this alignment is based on roll, pitch, and yaw errors. The roll sense when the aircraft or a spacecraft is moving off left and right side, that is called as a roll error. Pigeons in the nose part, they will make a up down movement, that is called pitch. Your errors created in the tail movement of the your aircraft. Okay, so this is the alignment errors. Now we need a complementary of this INS system on board with the GPS system, right? To make a perfect combination of navigation, we need a integration of these two systems like GPS and INS. See, the main shortcoming in the GPS is signal blockage for your received signals during the time of navigation. As I said in the earlier of my PPT, it has lot of errors, right? So these errors will give a blockage when the vehicle or an object is moving nearer to a tall buildings or a heavy forest, dense forest areas. The signal is coming from satellite may get blocked. So this is the one of the important problem we have in the satellite based navigation like a GPS, and another of your INS based navigation where the growth of position errors with respect to time. As the use of the sensors, if they introduce some errors in the initial part, the enlarged of the result of the error, it kept on enlarged. I mean, keep on increase as the time progress. Okay, so that is the main error we have on INS system. So in order to remove of these main shortcomings in the two navigation system, we can go for a integrated based navigation system where we have GPS and INS. It can be integrated with the concept called a Kalman filter. Okay, so this is the block diagram where I can use of my GPS system as well as INS system, right, with the help of my navigation based filter like a Kalman filter. See, the GPS, INS, both are navigation kind of systems, but they too have their own drawback. So to avoid of the two drawbacks, we are going for integrated system. In case any of the system goes on wrong, we are able to preserve our data and we can smoothly navigate of the objects. Okay, right. See, the inbuilt of the unit which I mentioned here is interactive multiple model and centered two filter smoothing techniques. See, the interactive multiple model is nothing but a combination of the Kalman filters. Kalman filter is a beautiful navigation filter which we have two kind of models. One is the Besserman model, another is an updated model, and we can go for a linear trajectory means Kalman filter is okay. In case you go for a non-linear trajectories, then we have to go for an advanced type Kalman filters, that is called unscented Kalman filters. Then again you need of a two kind of unscented Kalman filter to be integrated. Then you have to go for a IMM type of models, that integrated multiple model Kalman filters. Okay, there we use of this Kalman filter to reduce the noise. We can go for different type of smoothing techniques. Here I am using a two filter smoothing techniques to get off the precious value of your output. Okay, so this is the integration based system of GPS and INS. Okay, now the next of the topic, we are going for neural network based approach. Here only we are starting of our intelligent based navigation. See, this is a classical or a conventional method of integrating the navigation systems like a GPS and IMS. So what is the drawback in this system? Why we want to move to an intelligent based system? Because whenever you use of interactive multiple model like a Kalman phase of this system, the Kalman filter, or we can say the Kalman filter, somebody to pronounce that, it consists of a memory backup. Okay, so giving of memory when the time of doing measurement model and updated model, it requires a lot of memory space. So keeping up this memory space and preserving of all the data for the accumulative process of navigation, it's become so complex, right? And the next drawback is whenever you want to give inputs of your values, especially latitude, longitude, and in case of air vehicles and altitude values, what happened to that means the mapping of the inputs values, it's become very crucial, and also it's required a lot of complexity in the updated process of your measurement noise and then updated noise, right? So due to make of these unnecessary problems in the conventional method of integration, we are moving to a intelligent based navigation due to the advancement of your artificial neural networks and the advancement in the evolutionary algorithm techniques. Okay, so that is what I'm going from a conventional navigation system to an intelligent based navigation system. So far, what we studied or what we learn is that what is navigation, how to make a navigation with a system like GPS and INS, what are the drawback in the GPS navigation system and INS navigation system, how they have to be overcome by making of some integrative model like a Coleman based model, right? Now that model also has certain shortcomings. So to overcome those shortcomings, we are moving to a current technique of intelligent based navigation system. All right. Now we'll see that this intelligent navigation system is the a neural network based approach, right? Even in neural network based approach also we have certain drawback because in the existing type of the intelligent based neural network they are using a static type neural networks. I think you all know the feed forward networks. So for an example, you have a back propagation neural network, radial basis function neural networks. All those neural networks are has the nodes like input node, hidden node, output nodes in a static form. Because of these static natures, they are not able to make a flexible and a dynamic operations. Like as I said, as a drawback, like a static neural networks requires lot of fixed hidden nodes. Because of that, they are temporary memory space. Dynamic neurotics complex in the training process. Okay, so we need a new method which will complement of both these static networks and dynamic networks. So the new method consists of a dynamism to reduce the static nature of hidden nodes. The new methods we need like a feedback based neural networks, they called as a recurrent type neural networks, right? So the recurrent neural networks are become a popular neural networks for a intelligent navigation system where the nodes are dynamic in process and their operations also very simple when compared to the feed forward kind of neural networks, right? Here in the recurrent neural networks, we need of a feedback type mechanism. The outputs are again fed to input. The current of the autonomous vehicles are most of them are based on the this recurrent type of neural networks only. Right. Again, in the recurrent neural networks also, we have a different type of architectures like Ullman, Jordan, right, etc. Now, in my explanation of intelligent navigation, I considered Jordan network type RNN, which is a simple architecture. It's preferred for these GPS INS integration to reduce the topological and training complexity. Okay, right. Now, we will look at the certain performance analysis of this GPS INS integration using of this Jordan-based RNN neural networks, recurrent neural networks, by applying the evolutionary algorithm like genetic weight optimization algorithm. Okay, so here onwards, we are starting our intelligent-based navigation system. The objective is to analyze the performance of GPS INS integration using genetically weight optimized recurrent neural networks like a Jordan. See the system configuration, how we are changing from the Kalman filter based navigation, I mean a conventional based navigation to intelligent based navigation system during the time of my result process. I will show that system configuration later. Now let us see the theoretical approach of this concept. Okay. Next, this is the presentation outline. First, we have to see the structure, I mean, a architecture of Jordan neural networks, I mean, a recurrent neural networks. Then we have to discuss on genetically weight optimized neural networks, how it will be placed. Then what is the system configuration of this genetically weight optimized neural network based off the Jordan neural network? Then how the trajectories are considered as their movement of objects, right? maybe a linear trajectory or a non-linear trajectory, where a trajectory of aircraft vehicle means it goes from the one point to another point. So all that we have to discuss on the trajectory part, the resultant discussion, how the values are measured, how the vehicles are navigated in the airport, yeah. Then finally you have to conclude the concept. Okay, right. Now let us see. This is the structure of your Jordan neural network architecture. I mean, it's the example of recurrent neural net architecture. As you all know, in the recurrent neural networks, it has a conventional like a input layer, hidden layer, output layer, and the output layers are connected to the your context node via hidden layers. Okay, so for a simple architecture, here I considered only two nodes for the input layer and three nodes for the hidden layer and one node for the output layer. Okay. Here the output nodes are connected via a context node. It's like a supplementary node, or we can say it's like a alternative node for the hidden layer. Okay. So it's reducing the burden of the hidden layers during the concept of the neural network operation. So the context node will become like a supporting node, or we can say it's a supporting layer. In case if you keep up more than one nodes in the context layer, then it will become a layer. Okay, so this context layer is a like a supporting layer of the context. I mean, a hidden layer to make the work of the recurrent neural network to be a little bit faster than your normal feed forward networks. Okay, right. This is the structure. Here, all our input nodes are connected to the nodes of the hidden layer. Similarly, all the hidden nodes are connected to the nodes of the output layer via weight factors. Right. Similarly, in context nodes also connected to each nodes of the hidden layers. They also have weight factors. Right. Here, the weight factors I consider as W of xi is a weight factor of input to hidden, and hidden to output layer weight factors I consider as W of h by of I. Similarly, context node to the hidden I consider as W of c by I. Right. So with this of architecture, we are proceeding to the function of a Jordan neural network. The input to the hidden node is given here is, as you all know, the Z input which you are going to the hidden layer to a particular node is here is a summation of I of 1 to n x of I, that means the input values which are coming to the input node, and is connected by the weight factors, okay, which we have in the weight factor of your input node. Then it can be the summation of the inputs which are coming from the another set of the input node, like a context node, that also multiplied by input from the context node and the weight factor which are coming via context node. Okay, plus the value of bias. Bias is the a calibrating parameter which included in the hidden layer operation of your neural networks. Now, the output of the hidden node is given via Z is considered as an output via some activation function, right? The general activation function is whenever you go for hidden to output node, right? In any neural network operation, it will be a linear activation function, because I think you all know aware of that. Input to hidden node, you may use any activation functions for smoothing of our input values. Lot of activation functions are there, like bipolar, sigmoidal, tangential, like that, etc., etc. But whereas when you want to go for hidden to output layer, that is only one activation functions in most of the times. That is called linear activation function. That is what the linearization of neural networks started to happening. So the output which you got it from hidden node is the function of the your I mean activation function and the input value which you measured from the input node of the hidden. Okay. Now again, the output layer values are coming from the your hidden layer values plus the bias one. Now output of the net is y of g into y of in. Now the context layer is a delayed output layer, where the context layer input is c of it equal to y of t minus 1 because of the delay, right? These values are taken as a mathematical representation of your recurrent neural networks of Jordan type. Right. Now, how to implementation carry out in the Jordan networks? See, the input values which you are going to give it here as the input node values are nothing but the INS measurement values. They are taken as the input of your neural networks. In the target values, we are going to consider as the GPS values. Okay. The output of your neural networks is called as corrected INS values. The corrected INS value will be the corresponding output of the network when the input and target is supplied. Okay. These INS values and GPS values are taken as sample values in the numerical, and they are going to feed it as the input and the target output. And after the training of your neural networks, right, we are able to get the corresponding output, which will be considered as the a trained output of your navigation value for further application of the your vehicle navigation. Okay. Now, what are the performance measurement you are going to do it in the formula? Okay, during the function of your recurrent neural network operation based Jordan time. See, the first of the your measurement formula, that is called mean absolute error. That is equal to summation of I of 1 to n. That shows here is n is number of nodes which you are going to give it. Target minus predicted divided by m, where n is the number of data patterns. How many data patterns you are going to give it? Okay, that is considered as the average. Okay. See, for example, I will take of GPS values like 200 values, then it is called as 200. Okay, right. Now, to measure how successful fitting is achieved between the target and prediction, the R square static measurement is employed here. The R square is equal to 1 minus target I minus predicted square divided by summation of I of 1 to n, target minus predicted. See here, whenever your R square value is coming closer to 1, it shows that the fitting between your input and target is become better. So the parameter of your R square, that is a measuring parameter, metric parameter, where the value of R square is equal to 1 almost. That means the better fitting is occurred between of your target value and input value. Similarly, how much of CPU time is measured, okay, during the process of your training? How many epochs? Epochs means an iteration cycle is required when your neural networks is completed its operation during the time of system process. That tough training time also to be measured. Okay. So now you are going to train up your neural networks with the help of an algorithm, human evolutionary based algorithm that is called genetic algorithm, right? So these genetic algorithm based recurrent neural networks will make your navigation as an intelligent navigation. Okay. Now let us see the procedure for the genetic algorithm. Of course, this is the basic concept, but still some of them may not aware of that. So that's the reason I want to give the procedure for a genetic algorithm. The first, it start with the randomly generate initial population with a number of chromosomes, right? Then define a fitness function based on the error on the training of neural networks. So fitness function is playing a very important role. They like a membership function we have in the fuzzy logic. So based on the fitness function, right, the error which you are going to consider in the training of neural networks. Then calculate the fitness of each individual chromosome. Based on the fitness, select a pair of fit chromosomes for a combination process. Then perform crossover and mutation to generate new crossover. See, this crossover mutation, these are the internal cyclic process of genetic algorithms. Place the new chromosome in the new population. That is called the next generation. Like this, the process can be repeated. Repeat the step 4 until size of new population is equal to size of the initial population. Okay. Then replace the initial chromosome that's called as the parent with the new population that's called the offspring. Now go to step 3 until the termination condition is met. Termination condition will be the minimum value of error. Once you got the minimum error during of the training of neural network, you please stop the things. Otherwise, the process will be continued from this point number 3 of fitness of each individual chromosome. Again, based on the fitness, how to select a pair of fit chromosomes for a combination process. Then again, you have to perform a crossover mutation. Like that, it will be continued. So this is the process of genetic algorithm weight optimization. Now, let us say how to implementation of this genetic algorithm. First is you must set that how to find the chromosome, right? See, the chromosomes you are going to consider on these neural networks of your RNN-based Jordan is nothing but randomly chosen weights are taken and chromosome will be formed. Here the weight values can be taken randomly between 0 to 1. In case you take a higher value of weight value like a 0.9 or 0.8 like that, then what happened? The training time will become more. We need to go for a lot of iterations. In case the advantage is you will get a better mapping of your target value and input values. In other hand, when you go for a small value of weight factor selection, like say for example, 0.1, 0.3, 0.2, what happened? Iteration, I mean this architecture will give a faster operation. The iteration will be low, but the occurrence of your conversion, it's become what I called is not a small value, it's become a larger value. So conversion will not be proper when you go a low value of weight selection, whereas the process will be faster. In other hand, when you go for a higher value of the weight factor, conversion will be better, but the operation will become slow. Right. That's why you have to trade up that whether to go for a higher values or lower values. So you must sit on based on the requirement of your application. You can select of the right value in a random way. Now, objective function. This objective function of this genetic algorithm is defined based on the error value of time. Because in our process, we are going to make of target values and the input values. Between of this input and target, I mean the train value minus of your, I mean, sorry, original value minus train value, you have a error. So that error, based on that, you are going to take off your objective function. So the population with the least error value is taken as the best population. Okay. So this is the way you have to implement the chromosome concept of your genetic algorithm. Right. And this is the genetic algorithm cycle for your understanding purpose. I'm giving the a chart of this GA cycle like based on our earlier theoretical discussion. So you have to start the process of CA cycle with the current population. Then you have to evaluate the fitness. The fitness for more low error is achieved. Then you can stop the values. Otherwise, this can be continued with a selection of your parent chromosome and a new chromosome of your offspring, and they must be crossed over, then mutated. Then after the mutation, you have to find a new population. Crossover and mutations are important parameters we have in the genetic algorithm that we will discuss later. And once the new population is achieved, it can be compared to the current population. Then you have to evaluate the fitness. Like that, this process will be continued. Okay. Now, how to get the a chromosome formation in a Jordan type recurrent neural network? Now let us ask the earlier architecture we already found it. We know that. See here in the input layer are the input nodes. The red color nodes are called as the input nodes, which are aligned on the input layer, right? And these blue color nodes are called as the hidden layer nodes. Orange color node I have taken as the output node. The context node I am taken as the green node. Okay. So the layers are nothing but a combination of different nodes. Right. The other important thing is that in a neural networks, people may know that there will not be any interlinking between the nodes of the same layer. Nodes can be connected to only the nodes of the nearby layer, right? So the interconnection of the individual layer will not be permitted for any neural networks. The nodes are connected only with the nearby nodes layer. Okay, so in that point of view, the nodes of the input layers are connected to the nodes of the hidden layer, the nearby layer of hidden layer. Similarly, all the nodes present in the hidden layer can be connected to the output layer. Okay, right. See, for an understanding and simple analyzing purpose, I consider only the two nodes in the input layer and two nodes in the hidden layer, only one node in the output layer. See, the presence of the input node and output node are based on the value in which you are going to measure it. Okay. So here you are taking the input node as INS node for an INS values, and the output node of you are going to make it as a GPS value as a target, and then the corrected value as your corrected INS. Okay, now let us see the formation of chromosome. Here, the weight values from input to hidden layer of node 1 is A. Similarly, the weight value from the input node of your input layer first to the node of hidden node at the second of your hidden layer. So it is called as weight factor of B. Right. Similarly, the second node of your input layer to the first node of hidden layer, I considered the weight value as C. Similarly, the second node of input layer to second node of the hidden layer, I consider the weight value as D. Similarly, from hidden node to output layer 1, I consider weight value of G, and the hidden node of 2 to the output layer, I consider as the weight value H. Similarly, for context node also, we will form the weight values like E and F. So, combination of all these weight values, I will consider as the chromosome formation. Because, in a neural network based of operation, every time when you do a iteration process, the parameter which will undergo change is only a weight values. So I automatically select that the value of these weight factors, right? I consider as the chromosome, because each of iteration, these values only keep on changing. So one particular time when I get a minimum value of error, this is called the best fitness, I will get the weight values, which is my best chromosome of weight combination. In that case, I am forming my chromosome based on the weight values like A, B, C, D, E, F, G, H. Okay, with the combination of all the weight values, start from input to hidden, hidden to output, and output to context node. Okay, now we'll move on to the next slide. How to make the other process once you form the chromosome in the genetic algorithm application. The concept of crossover, it's nothing but the swapping of values between the parent chromosome to produce a offspring. See, actually, the crossover is to get the better fitness, because once the parent chromosome has a weaker spot of the weight combination, the weight combination must be made it to better when you go for a better offsprings. Example of there are so many crossovers are there, like multi-point crossover, single-point crossover, two-point crossover. But in our explanation, I consider it's a two-point crossover. In the two-point crossover, two random sets are taken, and the gene values are exchanged. See, the parent chromosome, what I consider here is A1, B1, C1, D1, E1, F1, G1, H1, I1, J1. Similarly, the next of the parent chromosome, I consider like that. Now, the genes of the T1, E1, F1 are randomly swapped, right? So, the new offspring is become now like that. A1, B1, C1, now D2, E2, F2, G1, H1, I1, J1. The second of offspring become A2, B2, C2, D1, E1, F1. Like a small swapping I'm doing between of my parent chromosome and offspring chromosome. See here, the crossover of your taken between the two-point crossover, because I consider only the two-way of crossover. In case you want to go for multi-point, that also possible, single point also possible. So based on your own requirement, you will do of your crossover operation. Right. Crossover is nothing but just a random sites taken of the gene values which are exchanged between your parent chromosomes to the offspring chromosome to get the better fitness of your target values. Right. Now, what is mutation? See, the mutation is nothing but a random changes in the chromosome. After crossover and mutation, the newly generated population should be placed in the new population pool, which has a better chromosome, which will give a better output of your corrected INS value with the minimum error. See, in case, let me say, the mutation is to create any uh, what I call any negative concept of your chromosomes. In case to give a better visibility of your new population, then it is virtually you are creating of mutations, right? So this through a virtual generation of mutations will further enhance or it will further strengthen of your new chromosome, which will going for the better opportunity of your offspring. Okay. See, this is the way you have to form the chromosome length for a neural networks. Here, I considered a network of backpropagation neural networks because it is coming under the feed-forward type neural networks. The other are nothing but recurrent type neural networks where we have a Elmon and Jordan type, right? But in our work, I consider only the Jordan. But for a comparison base, that's considered PPN and Elmon also. See, PPN, as I said, is a feed-forward neural networks. The feed-forward neural network, we don't need of any context layer because we never go for any feedback, right? I mean, in the layer formation, algorithm-wise, we'll go. Okay, so that we have only a input layer, signal layer, output layer. There is no context layer. Similarly, for the Elmon Jordan is like a recurrent type neural network. The difference between Elmon and Jordan is in the Jordan, the output is given to the your output given via context to given, whereas in the Elmon, the output will go to the input via context. But in our application, we discussed only the Jordan type recurrent neural networks. Okay, so now with this kind of the architecture I selected, the same of the node point, two nodes in the input and two nodes in the hidden and one node in the output and one node in the context. We go for Elmon and Jordan. The combination of your chromosome will be like this, right? Input node is 5, hidden node is 5. Whereas in PPN, I said we don't have any context node. That's what, that we don't have any node in the PPN. So number of output node is also here considered 1. In case, if you keep a PPN, you combine your weight factors, it will give a length of chromosome will be 30. Similarly, like in other architectures, the Elmon, Jordan, with the form of this node structure, the chromosome value will be come with the length of 55 and 35. Okay, that we have to see with the weight factor combinations. So this is the way you have to form the length of your chromosome. Right. Now, this is the system configuration which I want to show you is a replacement of your classical method of integration. See here, I'm using of the neural network based system. Of course, here I'm using of recurrent neural networks with the Jordan type, right? Here, I'm going to take my input from the inertial measurement unit, like INS mechanism, inertial navigation system I'm using. With that, I'm taking the values of my latitude, longitude, and altitude, and these position values are given as an input to the neural networks, right? Now, these inputs are given as the input of your input nodes. Hence, I have only here I considered latitude, longitude, and altitude. Of course, I am not going for the altitude here because as a simple concept, I consider only latitude and longitude. I selected only two input nodes. Okay. See, in the GPS, we are taking as a target values, which you are going to give it as the your target output. Okay. And this is also I consider as only two values like latitude and longitude because here also we consider latitude, longitude. So that is the reason in GPS also I consider latitude and longitude. What happened here in the mapping of your input and output will become very easy. Then we don't need of any memory, and also we no worry about the noise presence, and there is no problem of how to cancel the noise. All those problems we are eradicating when you go for this intelligent-based navigation system, right? See here, first you have to make a training. This violet arrow marks indicates how you are doing a training process. After the training process, right, you have to make it that your GPS is become outage. So the GPS value can be abruptly, it will be cut off. So the GPS values is lost. You assume that the GPS values are outage. Okay. So during the training process, you have a GPS values, but as of now, there is no input value of GPS because GPS become outage. What happened due to the training values you already had it in the neural networks? The training values are preserved, okay, due to the training process. These values are considered with your INS values, right? And now these GPS value of your earlier train can be subtracted with your position values of INS from the inputs. Any comparison, I mean your output of target minus trend of input can be subtracted here as a summation process. Now the value between these two error will become minimum, right? That shows that you have a better mapping of your output of GPS and your trade of INS. Then you get a output value here. This output value is called as the corrected INS value. Okay, so this is the way you have to do a configuration of system application for intelligent based navigation. Okay, now we'll see a result concept how you are taking of your experimental analysis of the research process. Now, I consider a linear trajectory of my vehicle of aircraft, which is moving from Mumbai to Bangalore, right? This is Google-based inputs. I can take it from this trajectory. Okay, I will take off my latitude and longitude values as INS values and also from a GPS values of satellite, right? And these values are considered as the input values and target values of my intelligent-based system configurations. Now, after getting of this input of latitude, longitude sample values, I will give that values to the input of training. And before that, train of my neural networks with the genetic algorithm, I have to check it whether the performance of GA in the Jordan topology is working or not. So I have to apply this genetic algorithm, the Jordan-based RNN. I have to see that whether my GA process is working or training properly. So this is the way how to check my Jordan error, the application of GA. What happened, the genetic algorithm, first the error will be higher, the later the error will be gradually will come down, slowly it will come closer to almost a zero in the final iteration, almost to zero. In a real time, will never come to zero. So once you have a training operation of genetic algorithm like that, it shows that you have a proper genetic algorithm training process you are undergoing on the Jordan networks. Once we're confirmed with this kind of graph in the error versus epoch generation, right? Now we'll go for giving your inputs values and your target values as an INS and GPS values of your measured trajectory. Okay. Now, after the process of your configuration, once you are ensure that your GA is working properly, and then you are giving off your GPS and INS values, then the final output of your comparison of neural networks by a GA weight optimization will be like that. See, in the normal backpropagation neural networks of feed forward, my CPU training time is 9 seconds, whereas in the Elman it is 7 seconds. For a Jordan it is 4 seconds. So this CPU training time are giving a minimum error of your iterations, like I showed in the earlier PPT. Then the mean absolute error parameter, it is very lesser for the Jordan when compared to Elman, and PPN it is slightly higher. Similarly, for R square, I said that these values come almost close to 1. So it shows that we have better mapping of your GPS and INS values with a better training of your GA. So from these values, it understand that GA has a better of your navigation ability than the Elmon and PPN architectures of neural networks. Right. Now, the comparison of neural networks by PPN and GA weight optimization. Right. I am applying of this PPN algorithm, back propagation neural network algorithm and genetic algorithm on these three architectures like PPN, back propagation neural networks, Elmon networks, and Jordan networks. These two are coming under recurrent neural networks. Right. Now, when I compare of this PPN algorithm and GA algorithm for the same system configuration, I found that CPU training time is 13 seconds here. In the Elmon, it will take 12 seconds, whereas in Jordan, it take only 9 seconds. When you are doing of GA-based operation, there the CPU training time is coming again to a lesser value, 9 seconds for a PPN. The PPN algorithm, it is 13 seconds, whereas for the G algorithm of say PPN architecture, we have 9 seconds only. For Elmon, it's coming down from 12 seconds to 7 seconds when you go for G algorithm than the normal PPN algorithm. For a Jordan, it's almost 4 seconds, okay, compared to 9 seconds of your PPN algorithm. Similarly, for mean absolute error also, it's giving a very lesser value. For Oscar, it's giving a very high value for a Jordan, okay, then compared to the your PPN algorithm. Of course, PPN, Jordan, and Elmon is giving 1 for R square, whereas in the Elmon, it has a better, for a PPN, it has a better, when you go for a GA-based algorithm operation of your RNN GA-based optimization techniques. Okay, so this is the result comparison of neural network, and I go for my PPN algorithm and GA algorithm for the architecture of neural network like PPN, Elmon, and Jordan. Okay, so from that, the result what we got and what we conclude is that recurrent networks of Jordan, even in recurrent networks, we have two types, Elmon and Jordan, but Jordan give better result than all other networks when accuracy is concerned. It's giving a better accuracy because, you know, the parameters like your R square, mean absolute error, they're all coming very good for a Jordan type of architecture. So we conclude that it's giving a better result. But both the recurrent networks, like Elmon and Jordan and PPN, are best fit for GPS INS integration, which is proved by Oscar value. Oscar value shows that almost Jordan is better, and this even Elmon and Pippin also is coming closer to 1, so that shows that it's giving a better fitting values. So when the efficiency is concerned, Jordan networks give better efficiency when compared to your Elmon and your PPN. Because in the mean absolute error, it only gives you a very high value, Jordan. So it has a better efficiency value when compared to the other of your architecture laws, Elmon and PPN. Okay. So this is the final conclusion we got it from the genetically optimized recurrent neural network based intelligent navigation. Right. Now we'll conclude that recurrent neural network like Elmon and Jordan with genetic weight optimization give better result than it is trained by standard PPN algorithm, backpropagation neural networks algorithm. For the GPS INS integration, recurrent neural networks provides best fit between the input and target values. Right. So with that, I will conclude now the GA-based RNN of intelligent navigation. Now we'll go on to the next of the topic. Here, the GPS INS integration of our navigation can be done on the same Jordan type network by PSO weight optimization algorithm. Only thing is that we optimize the algorithm of earlier integration of GPS INS with the help of your GA, the RN of Jordan. Whereas the same of the concept, I'm going to optimize the algorithm of PSO. That is the difference here. Now let us see how it can be taken in the PSO concept like an introduction, objective, particle swarm optimization learning. That is the expansion of your PSO. Our system configuration. Of course, system configuration is same like your earlier only. I like a GA-based optimization. Trajectory, here I may consider a trajectory of nonlinear also. How to get the simulation result. Then we'll see some of the performance metrics, how they are performing. Then we'll see the experimental result finally. Okay. Right. So to analyze the Jordan neural networks with the PSO learning algorithm in terms of performance parameter analysis for GPS-INS integration, like Jordan neural network architecture, we already found out on our earlier discussion, the same of architecture only. I'm going to use it for this PSO optimized navigation also. Okay. So here also the same architecture I'm using: input node, hidden node, output node, and then the context node. Same architecture. The combination of weight also the same procedure only I'm adapting here. Now, operate, then that kind of combination of weight and bias can be combined, and then it's considered the personal best. Okay. Now, the same way we have to see how to find the selection of the global best. Okay. Right. Say now the global best means the minimum value among the personal best. So it is nothing but G best of minimum value of WIX. It is nothing but the weight values goes from input to hidden node, and this is the bias value of the hidden layer. This is the minimum of hidden load to output layer weight factors. This is the minimum bias value of the output layer, and this is the minimum weight values goes from the context node to hidden node. So once you get the minimum of all these values, bias and weight values, then you can make it as a global best. You will declare as the global best value of your particle searching algorithm. Okay, now we will make certain comments on the inertial weight factor, because this is one of the parameter we are exclusively having only on PSO. Okay, this inertial weight factor will not come on genetic algorithm or other evolutionary algorithms. See, this PSO is based on the particle, I mean swarm-based algorithm, whereas genetic algorithm is based on the human evaluation algorithm. Okay, now the large inertia facilitate a global search. Right? Now, larger the weight value, it shows that greater global search ability. Smaller the weight value, it makes greater local search ability. Okay, so you must be clever enough to choose of your weight values between the larger W and smaller W to keep up with the local best as well as the global best. Okay. Now, this is the flow chart depicting the your BSO algorithm, like a star, initialize particle with a random position and velocity vectors. For each particle position, evaluate the fitness of better than the fitness of the personal best, then go for the personal best equal to particle, set best of the personal best as a global best, then update particle velocity and position, and finally you will get of the global best, which is the optimal solution. That time you will stop the things. Here, the loop until all particles exhaust. Similarly, this loop until the maximum iteration is happened. Okay, so this is a flow chart depicting of your PSO concept. Right. Now, comparison with other evolutionary computation techniques, unlike genetic algorithm, this evolutionary programming and evolutionary statistics in PSO, there is no selection operation. No crossover operation in PSO resembles mutations in evolutionary programming. In evolutionary programming, balance between the global and local search can be adjusted through the strategy parameter, while in PSO, the balance is achieved through the inertial weight factor. That is what we saw it in the earlier slide. So the PSO is slightly different from your other evolutionary programmings as well as the from genetic algorithms, because in genetic algorithms we have a crossover mutation like parameters, whereas in PSO we don't have all those things. Okay. Now, how to implement a PSO algorithm in a Jordan neural networks? This is the PSO algorithm which we are going to implement on this Jordan type RNN. Now, first take a step one, initialize the weight and initial context layer values to random values. As I said, how to set the random values in earlier also, you have to keep it always the values of the weight values between minimum to maximum, right? When you go for the maximum weight values, as I said, the convergence become a better, but the time taken of your neural network epochs will become more. The minimum weight values means conversion become worst, become poor. At the same time, the time taken will be better. It's become faster in operation, but conversion ways, it's become error ways, it's become worst in the output. Okay, so see that the weight values can be selected in between of your minimum to maximum. So you should do some kind of trade-off, depends on the application which you are going. Right now, while stopping condition is made to 3 to 14. Okay, for each training pair, do 4 to 14. Each input unit receives its input signal and transmit to all the units in the hidden layer. Each hidden unit receives its contact layer value also. Each hidden unit sum its weighted input signals is described by, well, how to find out the values of hidden node. It is nothing but the hidden node, you mind it, you have two kinds of inputs. One inputs coming from input nodes, other inputs coming from context node. So you have two kinds of the multiplication of values. One is input of your input node and weight values of input node, and input of context node and weight values of context node. This is the bias values of your hidden layer. Now, hidden node output is calculated after applying the activation function, that is z equal to f of z in. These values of this hidden layer output is given to a sum of weight input signal, and it is given as the input of your output layer. That is called y of in. Finally, the output of the output layer will be y of g yn. As I said, this g will be always the linear activation function. Now, the output node as a context layer value, which will be useful for the next iteration. The purpose of going the context layer or context layer is to remove, you cannot say that remove, to reduce the burden of your hidden layers and to smoothen the process speed to a minimum of complexity. Okay. See, now the each output unit receive a target value, and error your del of k, we can say, will be calculated as your target value minus train value. Okay. So as you have a better of mapping, definitely your error value will come to closer to zero value. Okay. Now the output unit update. How to update your bias and weight values? Now weight correction term can be updated. The del of Wi hidden weight factor is equal to input of your weight and inertial weight factors at t minus 1. Similarly, from the context node of personal best and your C2 R2, these are the velocity parameters and random value selection of your movement parameters, and global best minus W of I. Now, best correction term, that is called change in the bias term, also will have these kind of things. Therefore, finally, your weight of your new will be weight of old and the change in the weight factors. Similarly, for bias also, the new bias values of old bias and the change in the bias values. This is the output terms of the units combination. This is a hidden unit update of bias and weight value. This is same like your output node of the combinations. Here also we go for the same of your weight correction, bias correction, and finally you have a new value of weight factors and bias value of new value weight factors. And this is also your updated values, right? This is from your hidden to output. Okay. So you have to do two kinds of updation. One is from input to hidden node. There also you have to update your weight values as well as bias values. The second updation of your PSO is happened from hidden to output. There also you have to update of your weight values. Similarly, you have to update of the bias values. Finally, the context unit updates is weight as follows. So here also you have to make of context weight values. Similarly, your new values of the weight values. Okay. Now each term is related to inertial weight factors and the C1 R1 value parameters, personal best and global best. Do the step 6 to learn while stopping condition is false. Okay, so do a particle best updation. Okay, your personal best updation will be your personal best updation. It is greater than of your weight values. Otherwise, it will be coming to hidden layer weight factor t plus 1. Similarly, for personal weight value of bias, personal value weight factor of your output, personal weight values of bias of your output, finally you will get the personal weight value of your context. The same way, how to update your weight values and bias values of your stopping condition. Right. So at the last, you will get a global best updation like G best of minimum P best in the hidden load, as well as global best equal minimum best of the bias of the hidden node. Global best is the minimum personal best of the output node. Global best is the minimum bias best of the output node. Finally, you will get a global best is a minimum of all your personal best of your context node. So this iteration can be repeated from 12 to 14. Now, after PSO is applied, right, the system configuration is same like your earlier one. Here also we have the inertial measurement unit, global position unit. So the train values are here also the Jordan type neural networks, but the algorithm which you are using for training is here PSO. Right. Now, this values of GPS can be compared with the INS, and the error of your target value minus train value will be get it as a corrected INS value, which now it can be available for training of your object. I mean, your navigating the object, though the GPS will be on the outage. Okay, so this is the way you have to do a intelligent based navigation using of system configuration, right? This is a trajectory I am following. This is a linear trajectory I followed in the earlier GA-based operation. Non-linear trajectory also I can use that for an international aircraft application. But the trajectory wise, even it is linear and non-linear, doesn't make any change in the process of your operation. Similarly, in the output of your metrics. Okay. So this is the way I'm getting my graph, right? For a latitude, longitude, both are in degrees like an angular of gyroscope values. In altitude, I am going with the accelerometer with a kilometer, right? Almost INS, GPS, Elmon, Jordan, PPN, almost come closer. Only with a small variation, we can able to get the perfect values. As I know, Jordan is coming a closer value of your GPS values, okay, in all the types for latitude, altitude, and output of your latitude. See here, your time in minutes shows that how the training is happened, and this is all the degrees of latitude in the y-axis parameters. The x-axis in all the times it shows that time minutes in the neural networks process, CPU times. For a non-linear trajectory also, the same concept of graph is formed for a latitude, longitude, and altitude. So here you have a graph of your INS input, the target values. Then after the training of the values, once you got your trained output with the minimum error, then it's called Elman values, Jordan values, PPN. Three architectures you tried and we got the output. But in the presentation, I told only the Jordan type of architectures. Okay. But compared to all the things, this only giving a minimum value of the errors of that is called Elman, which is marked in the red or you can say orange color. See, the same way you want to put it in the latitude and longitude alone in the degrees for a Jordan output. Let us see the graph INS GPS Jordan. Your Jordan output almost is come closer to your GPS than INS after the training. And this is a three-dimensional way. I mean, I can go for latitude, longitude, as well as altitude. Right? Altitude, I will make it in a kilometer. Latitude, longitude, I will make it in a degree. Here also, when I make it of three-dimensional MATLAB calculation, I almost got both the GPS, INS, and trained of INS values with the corrected INS in the Jordan networks of the application of PSO will come almost closer. Okay, so with that, even GPS or INS will not give any input due to their errors. With the Jordan output of trained, we will be able to guide your vehicle in a proper way, right? In a continuous navigation, right? And these are the measurement parameters like mean square error. This is the formula which I used for that. Okay, I think you all know. Performance index is another matrix I calculated. The mean absolute error, sensitivity index, R square. So after applying of these values on path 1 and path 2, path 1 for linear trajectory and path 2 for non-linear trajectory, in all the case, I am getting Jordan will be give a better output than my ppn and lmon, right, for a latitude as well as longitude and latitude. See here, in a longitude also, the number of epochs for path 1 and path 2, the Jordan only giving a minimum path. It means that the epochs of minimum source, it's better in speed of operation. Jordan is giving a higher, speed. The operation of this Jordan is better when compared to PPN and Elman. Similarly, error-wise also, the mean square error, Jordan is giving better error, okay, compared to the PPN and Elman. Of course, they are coming closer only, but still it is showing the error in the kilometer-wise. R square also, it's giving a better errors, okay, for a longitude, for altitude, okay. So in the conclusion, we can say feed forward networks knowledge accumulation is poor because of this static node concept due to fixed topology and consuming more time to learning. In the recurrent networks, context layer performance leads to better knowledge accumulation. Among recurrent networks like Elmon and Jordan, Jordan network provides superior performance in terms of performance parameters. Since in Jordan network, context layer receives information from output layer instead of the hidden layer, this leads to better knowledge accumulation. So these are some of the references I used for my presentation. Thank you for giving me the this wonderful opportunity. So any queries, please, I'm welcome, sir.
Dear participants, if you have any queries, kindly unmute your mic and ask. Or else you can share it in the chat box. We will bring them to the presenter.
Sir, good evening, sir. This is Dinesh Kumar, sir.
Yeah, good evening, sir. Sir, any questions? I'm ready to answer it, sir.
Sir?
Yeah, yes, please.
Sir, can you hear me?
Yes, I'm hearing you.
Yes, sir. Yes, sir. Sir, really wonderful presentation, sir. First of all, I would like to thank for your excellent presentation. The concept of crossover and the few examples of two-point crossover is really helpful for the learners. And also the block diagram which you presented in the concept of system configuration with the GPS outage is very excellent. And also the insight about the practical PSO optimization, that means particle swarm optimization algorithm along with the weighted input is very useful, sir. Sir, I have one small doubt regarding the navigation process. Right
Yes,
now,
please.
in military applications, for the safety purposes, they will fix bugs in animals or human body or any soldiers, and they are going to track the movement of that particular human being or animals, whatever it is. Is there any drawback that is may cause any injuries or any kind of drawback is applicable while fixing any kind of sensors or something in the human body or animal's body?
Yeah, see, when you fix off any sensors in a human body, right, the problem is that the controlling operations. See, there only we have a concept called body area network, right? So when you send the signals in the body area networks through a wireless communication based concept, there is a possibility that the intruders also can interact with your signals, and anytime it may be blocked, right? So you may able to connect off any sensors through even a human body or animal body, right? The problem is that the intruders evaluation and the intruders possibility of connecting of your information, right? And it will be always dangerous, right? So even for intelligent navigation, you should also keep some kind of cyber security and some kind of spread spectrum technique concept to evaluate and to eradicate this kind of sensing into this information, right? Especially when you attach up some kind of sensors in the navigation process. So you must strengthen the security system. That is what I used to say, especially when you go for a wireless based communication in the navigation purpose. The concept of spread spectrum concept, there also we'll use of either a frequency hopping or a direct frequency hopping. You can use of this intruders concept, and you can use some kind of security mechanism in the base of your cyber concept, especially when you have a digital based information. Okay, so of course it has both the benefit as well as drawbacks, right?
Thank you, sir. Thank you so much, sir. Sir, and one more question I received from the participants through the chat box. Why is optimization used for machine learning? Which stage we are going to use? Why optimization used for machine learning? Which stage we are going to use?
See, optimization is used in machine learning, especially for neural network based systems. Generally, optimization is a techniques, okay, you can use in any system. A system has some kind of constraint, right? For an example, the purpose of optimization is to minimize those constraints and to get the best output from that system. We will normally go for optimization. So here the system means a neural network based system. The neural network based system is based on the artificial intelligence of our human brains. So it's need always some kind of training to get out. It never will give a perfect output of your operations. So in order to smoothen and in order to enhance the process, we need some evolutionary algorithm for in the form of training phase. So we have to go for a optimization algorithm. It's become very, very needed and it is very, very wanted of this server. So that is the reason we will always go for optimization algorithm for a machine learning purpose.
Thank you, sir. Thank you so much, sir. And one more question from the participant side. How the upper bound and lower bound number of population and number of iterations selected? How
Yes.
the upper bound and lower bound number of population and number of iterations selected?
See, see, number of iterations seems that means it seems that how much of your input to output process is going to happen, right? Starting from the initial population to your crossover mutation and the Springer population, or you can say as a new population. This complete of this four process will complete it. That is called one epoch process. That's called one training process. Okay. So this number of epochs is called as an iteration. It depends on how your values of the best, maybe a global best or a personal best. For an example, I have a target value, say for example 90, whereas my trained value is 70. What happened now? The iteration is one is finished, but now the difference is 20. Now again, I'm going for my next of iteration process. Now it's coming at the train value of 80, the target is 90. So now the difference is 10. Again, you go for a iteration process. That means second iteration. It is called second epoch. So now you are not able to come closer to 90. The third iteration, when you go, the system will become terminated. Since that there is no possibility of a further training, it means that you have to stop it your trained output only for the 80. It means the training itself is not allowed to go for further smoothening of your target with the trained output. So based on that, you have to choose of your number of epochs. I mean the training, right? It means how much of global best and the minimum personal best you are expecting, and the application will give. Based on that, you have to select the fitness function. For that point of view, the number of epochs is very much important for making of your system to be a trained one. Okay, so that is your first case. I mean the epochs. The second is what you call the upper bound and lower bound of your population. Is it? See, the population sense here, in my work of chromosome, I considered in the recurrent neural network is based on the weight values and bias values, of course, for the PSO. Whereas in the GA, when you go for weight values and bias values, because they are the two parameters, it will undergo variability when you tune off any neural networks. Okay, especially in the recurrent neural networks. Here we considered recurrent neural networks, right? So when you are having the a bound of population based on the weight values and bias values, you see that how much of your architecture is stick on to these weight values and bias values. See here for an example, for simple operations, I consider only two node of inputs and two hidden nodes and one output node and one context node. So within that, I restricted my weight values from input to hidden is 2 into 2, here 2 to 2, I mean like that 4. Similarly, from hidden to output node, one node to output and another hidden node to output. Here I restricted my weight values 2. Similarly, from context node, one node I selected, hidden node 2. So here also context node 1 to the hidden node 1, context node 1 to hidden node 2, I restricted with the two weight values. Right. So based on your requirement, you select off your weight values. Okay, of course, for the architecture base of your nodes, then you set up your upper bound and lower bounds. It's not like that you have to go for only minimum of input of nodes and hidden nodes, output nodes. But one thing I'm sure, based on the weight values and bias values of your architectures, you will restrict of your low bound and upper bound of your chromosome. That is the straight answer for that question. Yes, sir.
Thank you, sir. Thank you so much, sir. On behalf of St. Joseph College of Engineering, along with the team of ECE, along with the coordinator, sir, I really extend my heartfelt thank you for your excellent presentation, sir. Thank you, sir. Dear participants, if you have any queries, you can unmute your mic and interact with our resource person. Thank you all. We request all the participants to turn on your camera for the photo session. I request all the participants to kindly turn on your camera for the photo session. Dear participants, the feedback link is posted in the chat box. We request all the participants to submit your attendance through the feedback link. The feedback link is posted in the chat box. So we request all the participants to kindly fill the feedback and submit your attendance through this link. Thank you all. Thank you all for your continuous interest towards the learning. Thank you all. Thank you, sir. Expert, sir. Thank you, sir. Thank you very much. On behalf of St. Joseph College of Engineering, once again, I would like to thank our expert speaker, Dr. M. Malleswaran, sir, Head Department of Electronics and Communication Engineering, Anna University, Kanjipuram. Thank you, sir. Thank you for your valuable presence in virtual. Thank you so much, sir.
Thank you. Thank you so much for giving me this wonderful opportunity. So I hope that, shall I leave, sir?
Okay, sir. Thank you, sir.
Yeah, thank
Yes,
you.
sir. Yes, sir. Thank you, participants. We will start the next session within the 2 minutes of break. There is a short break for the 2 minutes, and we will start the next session. Thank you all.
ऊपर से नीचे कैसा आई हुआ? हाँ, कैसे निकाले ऊपर से?